Good morning, I'm Manuel Zarzo, and in this Unit 7 about ANOVA, I'm going to explain what is called factorial designs 2 power 2k. It means that all the factors are at 2 levels, which is a special case. So, as I was saying, it's represented like 2 power 2k. It means that we have k factors tested at 2 levels or variance. These experiments are easier because the number of trials resulting is lower, and also because the interpretation of results is much easier than in the case of factors at 3 levels. Okay, the effects of also the interactions are easy to interpret, but the problem is that quadratic effects cannot be studied. So if we want to study quadratic effects, we should include factors at 3 levels. So in this case, it's possible to calculate from the data 2 power 2k minus 1 effects. Okay, so this is the total number of effects that we can compute, and I'm going to explain this a bit more in detail. So we can compute k simple effects. All of them will have 1 degree of freedom. Then we can compute different kind of double interactions. Okay, actually the total number of double interaction is the combinatorial number k chooses 2. Okay, again, the double interactions will have 1 degree of freedom because we multiply the degrees of freedom of both factors. And also triple interactions, again, they will have 1 degree of freedom. The number of triple interactions is the combinatorial number k chooses 3. Okay, and so on. And the interaction of maximum order is always 1, so we always can check or study one interaction of the maximum order with all of the factor, which will have 1 degree of freedom. So in practice, triple interactions are not very common. In some cases they can appear, but this is not very often. So what is much more often is to have significant effects for simple effect and for double interactions. Okay. So, for example, imagine that we have a plan 2 power 2k, which means 4 factors at 2 levels. So in this case, it's possible to calculate 4 simple effects, 6 double interactions, 4 triple interactions, 1 quadruple interaction. So in total, 15 effects. But we can assume that most of them are not going to be statistically significant. Okay, and also remember that the degrees of freedom of the residual at least has to be 4, but if it is 10 or more, obviously it is much better. So imagine that we have 6 factors at 2 levels. So it's possible to estimate 63 effects, which is a lot of them. Okay, but most of them will be irrelevant. Basically, most of the interactions of order higher than 2 are not going to be statistically significant. Okay, in some cases it may happen, but it's not very common. So we can make this assumption. So it is possible to reduce the number of trials, sacrificing certain precision and this possibility to study high order interactions. Okay, so a good fractional factorial design should never confound simple effects between them, because simple effects appear quite often in practice, so they should never be confounded. If possible, a good fractional factorial design should try to avoid confusion between simple effects and double interactions, because sometimes we may have significant double interactions. They exist sometimes, and this confusion would result in a wrong interpretation of the results. And also, if possible, a good design should not confound double interactions between them, because they appear sometimes, although in some cases this condition cannot be accomplished. Okay, so what is a fractional factorial design 2 power 2k minus 1? Okay, so it means that k factors are tested at 2 levels, but with only half of the trials. Okay, so this is why we put like minus 1. Minus 1 means that we're performing half or 50% of the trials, which would be necessary compared with a complete design. Okay, so how can we build this kind of fractional design, which is very interesting because we're doing 50% of the trials, which means that we're saving 50% of the money, 50% of the time, which is very convenient. Okay, so we start with a complete 2 power 2k design. So we make all possible combinations of the different factors. Then if we work with these signs minus and plus, so then I multiply the sign of all factors. Okay, we'll show later with an example. Okay, and then we select those trials with the plus sign, or which would be equivalent, all of them with the minus sign. It doesn't matter. Okay, and that's it. Okay, so these are the steps to build this. So this kind of design is quite easy to make a fractional factorial design. For example, in this case, it's not possible to study the highest order interaction, okay, but this effect is likely to be the least important, okay, so it's not a major problem. The simple effect of a factor will be confounded with the chi-1 order interaction of the rest of the factors, which may be a problem, but not quite often. And the double interaction of two factors will be confounded with the chi-2 order interaction of the remaining factors. Okay, so this is something that we have to take into account to discuss if the experiment is convenient or not. Okay, then we have the following properties. Two effects, simple order interactions, will be confounded if their signs are coincident in all the trials. Okay, and for the case of interactions, we just have to multiply the signs of the factors. Well, remember that to study if one factor was confounded with a double interaction, or if a double interaction was confounded with another double interaction, there was a procedure that I explained in the previous video, which was like that several steps. But in this case, it's quite simple. We just multiply the signs and then we compare the signs. If the signs are exactly the same, we will say that they will be confounded, and if they are not the same, will not be confounded. Okay, so this is one example. Okay, so imagine that we have 4 factors at 2 levels. Okay, so first we should put like minus, plus, minus, plus, minus, plus, and so on. Okay, the same for B, we put minus, minus, plus, plus, minus, minus, plus, plus, and so on. Okay, and then so we start from the complete design. So which trials should we select to carry out just 50% of them? So then we make the product of all the signs, and in this case is plus, here the same, we make the product of the signs. Okay, it's like saying plus 1 multiplied by plus 1 is 1, plus 1 multiplied by minus 1 is minus 1, minus 1 multiplied by minus 1 is 1. Okay, so this is like the way to understand this. Okay, so if we make this kind of operations, we're always obtaining a plus or a plus 1 in this last column. So this is indicating that we have to choose those rows in this matrix where this product is plus. Okay, so this is the way to select the trials. We have to select those rows that this 4th interaction is the sign plus. Okay, this is the best possible design with 8 trials because each factor is tested 4 levels at a lower level, 4 times is tested 4 times at the higher level. Okay, the effect of each factor is orthogonal to the simple effect of the rest and also to the double interactions. Okay, and also we can check that the simple effect of A is orthogonal to the interaction of this. Okay, I mean this happens, so all simple effects are orthogonal to double interactions. I leave this for you as an exercise. Okay, but a drawback is that the simple effect of A is not orthogonal to the triple interaction. But as I was explaining before, it's not a major problem because we can assume that the effect of triple interaction is not important. So we can assume that this is equal to 0, there's no effect, and then if this effect of A is important, we will say that basically it is because of this factor. Okay, and then here I finish this special designs 2 power to k. Thank you.